Hey folks, this is Captain Jones here to talk to you about something called a race condition, which is a potential error in our code that we open ourselves up to when we are writing interrupts that are interacting with hardware devices, and we're not careful about how we do that. So our objectives today are to define this thing called race condition, what that is, and show you a couple of examples of it. So you have the ability to identify code that has the possibility of a race condition. And then I'll give you a tool so that when you're writing your code, you know how to account for those race conditions in your code. All right, so let's get started. Right here, we're going to take a look at an example piece of code from Chapter 9, which is a couple of lines of code from the trap service routine for out that's going to output a character to our display. And hopefully at this point, these couple of lines look very familiar. So these first two lines of code are just polling the display status register over and over again until it indicates to us that it's ready to receive new data. And when it is, we'll skip over this branch instruction and store the value that we want to show onto the display to the display data register. Let's assume for this example that on the same system we have the keyboard interrupt service routine that is echoing characters typed at the keyboard. So this is the same little sample interrupt service routine we saw from the previous lesson on memory mapped I/O. By virtue of the fact that these two programs are trying to access the display at the same time, we open ourselves up to some potential errors. So imagine, if you would, the sequence of code that looks kind of like this. So inside our out service routine, let's say we're sort of spinning here until the display status register indicates, yes, it's ready to receive new data. Let's say that this branch identifies that, we're not going to take the branch. We are about to proceed to this last line here where we're writing to the display data register. But before our program can do that, the keyboard registers an interrupt, and the interrupt service routine starts to execute. So you can imagine that maybe this program is about to write the letter capital C, but instead the user types lowercase t. That's what gets written to the display. By the time the service routine ends and comes back here, the display data register is not actually ready to receive that data. And so this store gets sort of silently ignored, and our trap service routine inadvertently failed in writing this character. We get sort of an erroneous output. This is one example of a race condition. The definition for this term is it's a quality of a code when the exact order of execution affects the program correctness. So for this program to have behaved correctly, in this case, the capital C and the T should have both been written to the display. But by virtue of these two programs kind of not interacting well with each other, and more specifically the fact that this interrupt service routine came, right after this branch instruction, we get some incorrect program behavior. So the book says, okay, this is there's a solution to this, and actually I'll say that what we call this series of code that has the potential for error if it gets interrupted, we call that a critical section. So the solution discussed in the book is to disable interrupts prior to that critical section, and then only once we're finished to sort of re-enable those interrupts. Now the book sort of shows an example of how this could be put to use. In the this service routine that is the service routine for the put string, I disagree with the book a little bit. So if we look at sort of the put string function, this is from 9.16. The book's answer to this problem is to say, okay, well let's disable our interrupts immediately prior to the character we want to send. We'll loop until that character is ready to get stored and is stored into the display data register, and then we'll re-enable our inputs. That might work for the out routine, since we're just storing a single character. But for something like put string, we open ourselves up to the possibility that in between characters being written to the display, as this program is sort of accessing the other characters in the string, interrupts can still occur, and so we might have we might be calling the put string service routine to display Kathmandu, I say, to the display, and in between the processing of this first character, if the user types lowercase t, that gets inserted in this string. And although the string itself, you could say, does come out on the display, we don't have the problem like we did potentially up here where we sort of miss characters. We still have the problem where there might be random letters that are inserted into this message. And so I would say that in actuality, this whole section here is our critical section. That once we start outputting this first character onto the display, we don't want anything else to display anything until this sentence is finished fully. Um, so so for me, the rule of thumb, actually, I'll jump down here, is anytime you are accessing the hardware from start to finish, that ends up being a bit of a critical section, and you need to protect that by disabling interrupts prior and enabling interrupts afterwards. There's one more complication we'll look at to kind of refine this solution just a little bit more. Let's imagine we have a user program that is doing some stuff, and right off the bat, it just disables interrupts. The programmers decided that they don't want interrupts to be triggered at all. So let's say we have our put string service routine that's written in this same fashion. So the user is going to call trap22 to output a message to the display. And let's say we're being good programmers, we're protecting this critical section. If we disable interrupts prior to outputting that message, and then at the end enable interrupts carte blanche, well, now we've actually turned interrupts on when they weren't on to begin with. We sort of disregarded the programmer's desire here. So so we don't necessarily want to across the board enable interrupts after this critical section. A slightly more nuanced solution is to instead start by getting the current status of the global interrupt enable bit. We'll store that in a variable somewhere. Then we'll disable interrupts and complete our critical section. And afterwards, we won't necessarily enable interrupts. We'll just restore the value of the global interrupt enable bit that we got initially. And so if initially interrupts were enabled, then at the end of this instruction here, they will be re-enabled. But if interrupts were off when we start here, when we restore the global interrupt enable, we are going to restore that bit to 0. We're going to restore that to its disabled status. And so you can kind of see that actually here in the in this example of the code where we are getting the current value of the status register. We are storing that value in R1. And so R1 has the original processor status register with global interrupts either enabled or disabled. R2 has the value with interrupts disabled. And so when we are if you follow through the rest of this code, then it's this line here, which is not necessarily enabling interrupts, but restoring the original value of the global interrupt enable. And so, if they were on to begin with, then they're back on, and if they're off, they stay off. Okay, so I mentioned before that basically, anytime you access the hardware, is kind of a good rule of thumb that you want to protect that with interrupts, disabling interrupts before and restoring whatever was the previous value after. And in the case of something like put string, I would make the argument that that hardware access starts from the first character written and doesn't end until the last character written. So from start to finish, the access for that hardware needs to be is a critical section that needs to be protected. Although more broadly, you could probably say that any part of your code that might get messed up if it's interrupted by any other interrupt, that becomes a critical section. So that's kind of the more broad way to think about this, the problem of race conditions. Okay, so today we talked about the concept of a race condition, which is when the exact order of execution affects the program correctness. We saw a couple examples of how a race condition could provide us with erroneous code if we have the out service routine that gets interrupted by the keyboard ISR that's echoing a character. We might actually miss a character if that ISR comes at sort of the most inopportune time. And then similarly for our put string, even if we disable interrupts around us placing a character on the display, we could still get what I would say is erroneous program behavior unless we protect the entire memory access by sort of turning off interrupts before and re-enabling them after. And then we sort of finished up with a slightly more nuanced solution. Since interrupts might have been disabled initially, we don't necessarily turn interrupts off at the start and turn them back on at the end. Instead, our best solution to deal with race conditions is after we've identified this critical section, which in most of the programs you're right, it's just going to be anytime you are accessing the hardware. What we'll do initially is get the value of the global interrupt enable, or you can see in the case of the book, we're just getting the entire processor status register. We'll disable interrupts, we'll execute our critical section, and then at the end we'll restore whatever was the original value in the processor status register to put the system kind of back into its original state. All right, folks, that's all I got. I'll see you next time.